Welcome to your next oceanography lesson on waves. And I have a couple pictures of waves here. I have a classic breaking wave at the top. I have some small capillary waves, they're called, on the lower right with the bird. And then on the lower left, I have a picture of the Santa Monica Pier. And we're going to talk a little bit about how you could stand out on the pier and watch waves go by and figure out some things about how deep the motion is below them. So here's an outline of what I'm going to talk about. And for this video, I'm going to cover what is a wave, including what the parts of the wave are called, how motion is actually transmitted through water, and something called the wave base. We'll then move on to how waves interact with the coastline, talking about something called refraction, longshore transport of water and sand, and how waves actually reshape the coastline. And that will be the end of this video. In the next video, we'll pick up with this last topic of erosion and deposition. So what is a wave? Well, a wave is actually moving energy. Now, if I had a slinky here, I would show you. Sometimes people use slinkies as example of waves. So if you have a slinky and you knock one end of it, and then a wave goes all the way to the other end of the slinky, well, the parts of the slinky move a little bit, but the wave travels all the way across it. And that's what a wave is. It's energy moving through something else. In this case, it moves through the ocean water. Where does that energy come from? Well, it comes from storms and the wind created by storms. The energy is carried all the way from wherever the storms originate through the ocean all the way to the shoreline and the beaches. And then at the shorelines and beaches, this energy is transformed into erosional energy and energy that moves sand. So the picture below here shows a cartoon wave, but it has some important parts of a wave that I want you to learn. These could be thought of as vocabulary terms if you want, but this is something that I would expect you to know if I ask you something about the height of the wave or the wavelength. These are the parts I'd like you to know. So let's start with the crest, which is the highest point in a wave, and the trough, which is the lowest point. Now there's a line across the middle here that's horizontal called the mean water level. We're just going to call that kind of the 0 point. So if there were no waves, the water would be exactly at that point. So we have crest and troughs. Now wavelengths are the length of one complete wave or one cycle. So it can be, as shown here, from crest to crest. It could be trough to trough. And then down here, it's showing a wavelength sort of from the point where the wave crosses the mean water level and crosses it again. As long as it involves one complete cycle of patterns of the waveform, it is a wavelength. We then have the wave height, which is the distance from the crest to the trough. And then the amplitude, which we're going to use not just when we talk about water waves, but also when we talk about seismic or earthquake waves, something called the amplitude. And that is the deviation from the wave from the mean water level or the 0 point to a crest or to a trough. So those are 5 terms I'd like you to understand about the parts of a wave. So how do things move when waves pass by them? Well, water does not just move from the ocean all the way to the beach. Otherwise, all the water would pile up at the shore. Instead, the wave moves through the water, and the water moves in what's called an orbital motion. If you look at this picture to the right, here's a little toy boat, and the wave is moving through the water from left to right. And if you just watched the boat, you would see that as the boat goes up and then eventually over the wave, and then the wave passes by it, it's actually making an orbital motion. It's not really moving left to right like the wave motion is. It's just moving in a circle. This is called orbital motion or an orbital path. And if we look at a wave sideways, if we take a slice through it, this orbital motion is shown here. And it, in fact, it decreases with depth. So if you were a diver and you went below the ocean surface where there were a lot of waves, you'd eventually get to a depth where you wouldn't notice any motion because the waves have stopped. So the waves are a surface feature. And it turns out there's a very distinct depth at which this wave motion, this orbital motion, stops. It's called the wave base. And below the wave base, there would be no movement of water. The wave base is half of the wavelength, or the wavelength divided by 2, and sometimes we use L for the wavelength. Waves that are in water deeper than the wave base are called deep water waves, and most of the ocean has deep water waves. So here's a little cartoon showing waves coming from left to right, from deep water onto the shore. And what you can see out here, we have the wave base indicated with this dotted line, and it happens to be half of the wavelength, which would be, for example, crest to crest. And these are called deep water waves. And it says here they have a constant wavelength. We're not going to worry too much about some of the details on these figures because this is really a topic that you would learn in an oceanography course. You'd learn a lot more detail about waves. And we're just going to kind of go over the surface, so to speak. No pun intended. So deep water waves are deeper than the wave base. All right, now here's my Santa Monica Pier question. A student, imagine, is standing at the end of the Santa Monica Pier watching the waves pass the pier supports. So you can look down here and you can watch waves pass by. This person, this student, also sees some surfers, and so they're able to estimate the wavelength of the waves. So perhaps they know the length of your average surfboard, and they're using that sort of as a measuring stick. And they estimate that the distance between two wave crests is about 30 meters. So my question to you is, if the wavelength is 30 meters, how deep is the wave base? How deep would you have to go till you no longer feel the motion at all associated with the waves? The equation, again, is the wave base is half of the wavelength. So the wavelength is 30 meters. The wave base would be 15 meters. So you would have to dive 15 meters below the surface not to feel any effect of the waves. Let's move on to shallow water waves. As you might imagine, these are waves that are shallower than the wave base. And what happens in this case is this orbital motion at the base of the waves starts to interfere with the seafloor. And we sometimes say that waves touch bottom at this point. Now what happens is a couple of different things. First of all, the speed or velocity decreases. They slow down. It's almost like a hurricane going onto land from open ocean, right? It has some friction with the surface and it slows down. Another thing that happens is the wave height increases. So we have the waves starting to drag and feel bottom, and the wave height starts to increase. The wavelengths get closer and closer together. So I'm summarizing here what happens as a wave approaches the shoreline. So the wave enters shallow water, which again is defined by less than half the wavelength, so the wave base or shallower, touches bottom, friction slows the wave down, the wavelength decreases, the waves start to bunch together, the wave height increases, and eventually at a certain ratio of height to wavelength, the waves actually break. And this is why waves break at the coast and don't break out in the middle of the open ocean, because of this phenomenon, this interaction with the seafloor. Okay, so that was the first part of our discussion. We're now going to move on to waves and what happens when they hit the coastline. The first thing that happens is waves tend to bend parallel to the shore. If you've been to the beach, you've noticed probably that the waves seem to be coming pretty parallel to the beach, right? They're pretty parallel to the shoreline. But most waves out in the open ocean don't happen to be traveling in that direction. Here I have a little cartoon, and let's say the wind direction is like this at a high angle to the land. And so the waves are coming in perpendicular to the wave direction because the wave is just sending that energy forward. And so this would be a wave crest and another wave crest, and there would be a trough in between. So that's just the way that they're illustrating in this diagram. So out here we have deep water waves, and then this dashed line is representing where the wave base equals the depth. And so if you get closer to the shore than this dashed line, now the wave is feeling bottom and it's starting to slow down. And as it slows down, it starts to bend. It starts to refract parallel to the shoreline. So the wave approaches at an angle generally, and part of the wave in the shallow water slows down. The part in the deep water keeps going, and that's what's shown in these red arrows for this particular wave right here. and it refracts, it bends parallel to the shore. And what happens as a result is we have movement of water in general, in this case, from left to right, or in the direction down the shore from the wind. This is an example of what that looks like. So here's the shore, and the waves look pretty parallel, but they're actually coming in at a higher angle than it appears at the shore. The result of the longshore transport or movement is a zigzag motion of the sand up and down the coast parallel to the longshore current, and this is called beach drift. And the longshore current offshore is not always very obvious, although you might have noticed it if you've ever gone to the beach and you parked your umbrella and your cooler and everything, and then you went out to play around in the waves, and some time passed, and then you went to look back for your cooler, and it seemed to have moved. And in fact, it seems down far from the beach from where you first went into the water. But that was because you moved with the longshore current without really realizing it. So where does the beach sand come from? Think about that. If you answered it comes from offshore in the deep part of the ocean, then you are wrong. However, you have answered what 99% of the people think is true, because it looks like it, right? You go to the beach, sand seems to be getting pushed up onto the beach and back out and back and forth. But that's not where the sand comes from. The sand actually comes from the land, from rivers that bring sand down to the beaches. So here we have these 4 arrows along the Southern California coastline, and they represent beach compartments. And these are the 3 parts that get sand from the land out to the ocean. The first part is the river. Rivers bring the sand from the land and dump it at the ocean. Then the beaches, where the longshore transport, which is shown here in the red arrow, moves the sand eventually down the beach. And then offshore, something that you can't see without having stripped away all the water, is that there are these submarine canyons offshore into which the beach sand eventually goes. So the sand does not come from the ocean, it comes from the land, and it gets worked its way along the coast. One last thing before we end this video is that this refraction also helps to shape the coastline, and actually it helps to smooth the coastline. So in places where there's something jutting out into the water, like what's called a headland, it gets shallower quickly here, and those waves bend towards that piece of land that's jutting out. And wave action is concentrated here, it's high energy, and it winds up breaking down and breaking back eventually the headlands. The opposite happens where there are these recesses or these bays. The waves come in very gradually, and they gently reach the shoreline without a lot of energy being dissipated, and they tend to deposit sand out here, whereas out here they're removing it. So next video we will move on to the last topic of erosion and deposition.